Number 4 asks us to consider the differential equation 2x minus y. 4a asks us to sketch a slope graph and a solution curve that passes through the point 0, 1. Note, use the axes provided in the pink test booklet. First off, don't write your answer inside the booklet that has the questions. Write it in the answer sheet so you actually get the point. Now, I know slope fields are from a long time ago in AB, but bear with me. A slope field is exactly what it sounds like, a field full of all the slopes of the graph. So, when you first start out, let's say you start out with 0, 0. You plug in 0, 0 into this equation, and the slope that you get is 0. You do that with 1, 0, you plug it in, and you get that the slope is 2. You keep doing that for the entire graph and make sure you've filled out every single dot and no more. Once you've filled out the entire graph, make sure you don't forget to sketch the solution curve as well. This one passes through the point 0, 1. Try to make it as accurate as possible, but if it's not the end of the world. (4b) tells us that the solution that passes through the point 0, 1, the one that we sketched before, has the local minimum as at x equals ln 3/2. What is the y-coordinate of this local minimum? Now, this is a very straightforward problem. They already give you the derivative, so you know that a local minimum is when the derivative is equal to 0. So you set dy over dx, which is equal to 2x minus y, equal to 0. Now, the hardest part of this problem is probably just the setup. Once you have this, you can do dy equals y, since you add the y onto this side, and since the x equals ln 3/2, the y equals 2 ln 3/2. And that's your answer. Part C says, let y that equals f of x be the particular solution to the given differential equation with the initial condition f of 0 equals 1, using Euler's method, starting at x equals 0 with two steps of equal size to approximate f of negative 0.4. Show the work that leads to your answer. Now, a first common mistake for this question is pronouncing it Euler's method instead of Euler's method. Never do that again. Now that we got that out of the way, let's start with the actual problem. They tell us that we're starting from 0 to negative 0.4. So you have to realize that we're going backwards from 0 to negative 0.4. So delta x must equal a negative number. In this case, it tells us that we have to use two steps of equal size. So if you do 1 minus 0.4 divided by 2, you get that the delta x will equal 0.2. Make sure that it's negative. Now, to start off, I like to do it in a very systematic way, kind of like a table. We start with f prime of whatever the number is, and then f prime of the number times delta x plus y value, and then you write the point with x and y. This way it's very organized. I know when to stop. So they tell us to start with the initial condition of f of 0 equals 1. This means that when you plug it into the differential equation, dy over dx equals 2x minus y, you use the f of 0 equals 1. If you plug in of f prime 0, which is the slope, you get negative 1. Now we have f prime of 0, negative 1, multiplied by delta x, which is the width, of negative 0.2, and then you add the y value, which is 1, since f of 0 equals 1. Now all of this equals 1.2. Now this is not a calculator problem, so bear with me, you'll have to do some algebra. So the final point will be negative 0.2 comma 1.2. And you know that the x value is negative 0.2 because that's what the width is, delta x. So every time you just have to subtract 0.2 from 0. Now the next step will be from f prime of negative 0.2. You use this point to plug into dy over dx, and you get negative 1.6. Now you multiply negative 1.6 times delta x, and then you add the y value that's up here, and you get 1.52. And so the point is negative 0.4 comma 1.52. And you see you've already reached negative 0.4, so 1.52 is your final answer. And so finally we get to part D. It asks us to find the second derivative in terms of x and y. Then determine whether the approximation found in part C is less than or greater than f of negative 0.4 and explain your reasoning, obviously. Always explain your reasoning. Even if it doesn't ask you to, do it just to be safe. Now, with the first part of the problem, it asks us to find the second derivatives in terms of x and y. So make sure you don't leave any x primes or y primes in the equation. You have dy over dx equals 2x minus y. If you take the derivative of that, you get 2x, just 2 minus y prime. Make sure you remember this y prime and don't add in an x prime like I did, since it's with respect to x, so the x just goes away. Next you have y prime, so you just plug in the original derivative back in, and you get 2 minus 2x plus y. Since it's asking whether the approximation is less than or greater, you know that this is always asking for you to plug something into the second derivative. If it's positive, then it means it's concave up. If it's negative, then it means it's concave down. And so if it's concave up or down, you can then use the approximation to see that if it would be over or under. Now this problem might seem a little bit tricky at first since you don't have the actual y value to plug into the second derivative. But if you look at it in a greater perspective, you can see that your x value is always going to be negative since it's negative 0.4, and that the y value that you approximated is 1.52. So that's also going to be positive. If you have a negative x value and a positive y value, you're going to be in the second quadrant. If you know that and you try to substitute some sort of negative or positive into the second derivative, you can find some sort of answer. You see if x is always negative number, and y is a positive number, this cancels out and becomes positive. And so therefore your entire second derivative is going to be bigger than 0, which is positive. Now if we said that if it's bigger than 0 and it's positive, then it's concave up, and that the linear approximation is going to be less than the actual value. Now that you have your answer, what you don't want to say is just that it's an under approximation. Since it explicitly asks you for justification, you have to justify it. There's no reason not to. Your justification is going to be something along the lines of, since the second derivative is always positive in the second quadrant, all solution curves in quadrant 2 are concave up. Therefore, the approximation is an underestimate. If you need any extra help, I'll have worksheets and websites in the description box below. See you next time!